And we need a comfort level, a high comfort level of floating point arithmetic, essentially. So I just stuck the SI prefixes up there for a reminder. Most of you will have seen them a number of times by now. Starting from somewhere down in the low, as the meter is a fundamental in this, we go all the way up into 1, 2, 3, up to big numbers like 10 to the 15th. 10 to the 18th is a number I want to particularly use a lot of tonight. That's an exa, and I'm going to use it in terms of energy as an exajoule, because it turns out to be a very convenient number. U.S. energy usage in a year tends to be about 100 exajoules. So when you think of an exajoule as 1% of the U.S. energy use, about 10% of Canadian energy use, and I think the U.S. energy use somewhere fits into about 30% of world use. So you have 3 to 3.5 exajoules is, or 3 to 350 exajoules is the total world use of energy. So very basic numbers. You just got to realize you're dealing with a lot of zeros after it. But in terms of an ease of trying to do it, it's a say that that's where we're going to work. Now let's move over to a look at energy as a broader concept. So I pulled out one definition from Google just for the very formal definition of it: the capacity of the physical system to perform work. Energy exists in the usual heat, kinetic potential, etc. And the various bits and pieces about it which you can read, and the unit for it is a joule. The SI unit, but of course there are a large number of other units in it, and electron volt being one of them that I tend to use fairly frequently, or mega electron volts, etc. And now we'll look at it from a more practical point of view, as I'll say. It's a bit of a tricky concept. We hear it discussed routinely, but one of the really interesting aspects from a point of view of energy usage at the level of total usage of a country or total world use or stuff like that. Well, the real main forms of energy that are practical from a point of view of large usage are the chemical energy of 2 atoms of oxygen combining with 1 of carbon, or hydrogen combining with oxygen to produce water. That's basically the main source of energy, a practical source of energy at the level of the world, essentially. And then the 1 or 2 others that are quite significant is again fission. That's our reactors, of course. That's the whole business of atomic energy, is splitting the atom inside in a controlled manner inside of the vessel. And you note on that you're just about 200 million electron volts, so that's 2 million times higher than a typical chemical reaction. So that's why the volumes of material used are much, much less. And then fusion is basically the energy of the stars, and that's where deuterium and tritium are fused together under very, very conditions of high temperature and high pressure. And you end up getting 17.6, again, million electron volts of energy from one reaction of fusion. So those are really the main reactions that actually produce energy that are used either on the Earth directly in the terms of chemical energy or the fission energy, and then all the energy coming from the solar irradiation from the sun is of course coming from fusion. So, and again, I've restated these because these really are a very important aspect of energy. The practical sources of energy at the world level are basically fission, fusion at the solar level, and then the molecular energies one gets. 13.6 eV is basically an ionization, so that's the energy required to remove an electron from a simple thing like hydrogen. And all the other reactions that are important from a point of view of producing energy are at the levels of bond energy, so the few electron volts per molecule. And on this one, again, I cut this one out from some website. It's got 1/40th, and that's rather important. That's the energy of an ensemble of, say, neutrons in a reactor. The so-called thermal energy is about 1/40th, or 0.025 eV. So, and again, that's the sort of the rate of energy of molecules floating around an air around us. So that gives you the scale from all the way from 200 MeV down to 0.025 MeV. EV, I should say. So that's like 7 orders of magnitude or more. And one other little item on there, in physics we tend to use electron volts. In chemistry, often we use the energy of a mole of electrons, and that's basically this 96 kilojoules per mole or 23 kilocalories per mole. I have a lot more trouble remembering those numbers. So now let's do a simple, and again an approximate example. This is the sort of thing I might do. I'm out taking my dog for a walk and trying to figure out, somebody asks me a question somewhere and it'll come back and I'll say, gee, this is the answer to that. And so, without actually knowing the numbers, I'll sit there and say, well, if I want to say, for example, I might want to figure out how much coal does it take for a power plant burning, in a whole day's time or a whole year's time. Well, with the next two slides, we're going to do that in a quite simple fashion. We use, in C to the pants, a guesstimate, 5 electron volts per reaction, because we've got two different oxygens, both forming bonds with the carbon, so it's probably going to be, and we know that the carbon dioxide molecule is a very strong bond, so it isn't easily broken up. So it's probably going to be 4 or 5 eV, maybe a little bit higher. So we use that as a rough starting point. Now we come back to one of those numbers that I mentioned at the beginning of the thing, good old Avogadro's number. We basically, in a mole, we're going to have basically that many atoms, and we're going to have them reacting with about 4 or 5 eV or so per atom. Come up with a number like 23 times 10 to the 24th electron volts for each mole of that material reacting. And we multiply that again by the charge on the electron, and the joules per electron volt, and we end up with a number like 400,000 joules per mole. Very quick and easy approximation. It's arithmetic. It's basically multiplying 2 or 3 numbers, and you can basically do it to 10% sort of accuracy, so you don't worry about carrying decimal places. You take first digits on anything. And in the process of reacting that, you're producing 22.4 liters of carbon dioxide at standard temperature and pressure. So again, basic stuff. But now we'll see the question I was posing. Let's see what we want to do with that. Well, we'll pose an interesting question. We'll run a large coal plant, 1,000 megawatt thermal coal plant, which is typical. I think that's higher than a lot of the coal plants, but the newer ones tend to be running up in the range of 1,000 megawatts. Now, 1,000 megawatts of electricity requires almost 3,000 megawatts of thermal energy, because there's only about a 33 to 35% efficiency, except for the very modern coal plants that get upwards of 40%. So it means you've got to put in 3,000 megawatts of heat energy to get the 1,000 megawatts of electron energy, or electric energy out of it. So, but the 33% efficiency. So that tells us how much energy we're using. We now put in that, we convert it to joules per second, we multiply by the number of seconds in an hour and the number of hours in a day, and we come up with a number of so many joules per day. Very straightforward. And then from the previous slide, we've shown that 12 grams of carbon, which is 1 mole, produces about 4 times 10 to the 5th joules of energy, or 1 gram produces that number, 3 times 10 to the 4th. Therefore, our electric plant, which we've shown here, is the order of a few times 10 to the 14 joules a day, and we just divide that number up. We come up with something like 10 to 10 grams per day, or 10 million kilograms. To put that into perspective of what it would look like, it's about 100 railway cars a day. So our electric plant to actually run, producing 1,000 megawatts of electricity, is bringing in about 100 railway cars each day of coal to fire that up. So that gives you, from very simple principles, 2 slides are basically derived from a few electron volts per atom up to using 100 railway cars of coal a day to run the coal plant. Pretty basic. It's arithmetic, and it's powerful, because that, someone asks you how much coal to run it, you would have to think a while, but it actually doesn't take that much.